Okay, welcome everyone to the IAMP seminar, which is a biweekly seminar series run by the IAMP. Today, it's our great pleasure to have Simon Becker from ETH, who is going to tell us about moire materials. So, Simon, please take it away.
Thank you, Ian. Thank you also to the other organizers for having me and for setting this up. Yeah, so I'm going to tell you a bit about what these moire materials, what's that about. Um, and the way I want to start is with, so, okay, nowadays it has become, a wide range of sort of materials that people study, 2D materials mostly. But the material that sort of got everything started was graphene, and graphene is just this two-dimensional material that has this honeycomb structure that only consists of carbon atoms. You can sort of extract it famously from your average pencil by by using Scotch tape and just ripping it off. So this is the structure of graphite, essentially stacked layers of graphene if you want. And then this 2D material is graphene and is sort of in some sense the basis for what this sort of new direction in material science in some sense is about. So just to give you an idea of the distances, even in graphite versus graphene. So this is sort of the atomic distance, 1.86 angstrom in the graphene between these atoms, and this is sort of the vertical distance between the individual sheets in the graphite. Before I tell you what these moire materials are about, just one more comment. So when people first analyze graphene, I mean analyzing sort of multiple layers of graphene, so maybe not like in graphite where you have a lot of them, but let's say bilayer graphene, so two sheets of graphene on top of each other, was a sort of very popular thing to do. And what people realized is that there's actually an energetic difference between just placing two layers of graphene perfectly on top of each other, which is called the AA stacking here. So you see it sort of illustrated by this red and blue, okay, versus the AB stacking, where you have this sort of displacement between these different sheets, okay? And so these are just some numbers I took from this article in 2015. So it turns out that so this is the energy you need to sort of extract one electron. So what this is saying is that this one here is much more stable than this one here. Okay, so somehow even if you just have two sheets of graphene, you just put them on top of each other, and you ask yourself which is the most stable configuration. It turns out that this AB stacking is much more stable than the AA stacking. All right. Okay, so what these moire materials are about, and moire is just, well, it's just an old word from sort of clothing, I guess, where different pieces of wool were placed on top of each other and slightly displaced so that you get this moire pattern. So what this is about is you have these two sheets of graphene, let's say, and again, I think this field has moved on from the graphene now quite rapidly. So there are many more directions or many more materials you can explore. But how it started is really that people looked at two sheets of graphene and they slightly twisted them against each other, right? So you see this red lattice here. This is one honeycomb lattice, and then you see the blue lattice here, and these are both graphene sheets, but they are twisted against each other, okay? And that's the basic effect. And what that does, in some sense, is that it gives you this sort of large honeycomb structure that you see here, and this is called the moire pattern, okay? And this moire pattern, so it also seems to be again quite obviously a honeycomb lattice again. So one of the basic effects that it just does is that you get larger fundamental cells, right? Whereas otherwise you're sort of stuck with your atomic distance fundamental cell. You now have a way to design materials in a quite natural way that that have just very large fundamental cells. And I'll come back to that, how that is actually useful in many of the effects that we see in these moire materials. Okay, and so the fundamental cell, in some sense, is proportional to 1 over the twisting angle. So meaning small twisting angles, then these honeycombs will essentially, so they will grow as the twisting angle goes to 0. They will grow like 1 over theta. And of course, since this is sort of mathematical physics, this might be an immediate objection that, okay, whether there actually exists a fundamental cell when you twist two lattices, right? Because, in in general mathematics, there might not be a commensurate fundamental cell now once you have two lattices and you've twisted them. So that's true. But what I'm talking about here is really the sort of visual fundamental cell. So your eye will never be able to tell me if, this is actually commensurate or incommensurate, okay? So what I'm talking about is that when you have these two lattices, you twist them, you will always think, okay, so the fundamental cell essentially is like 1 over theta, okay, even if it's not commensurate. All right, and so this entire business of regions of so just before I told you something about this AA stacking where you perfectly align, and you see this, for example, here at the center, right, where the red and blue, they are just on top of each other. And then you see these AB regions, I would call them, so where you have this sort of mismatch between the different lattices, and that's what you see here, okay? And there is actually an effect of that. So this kind of picture is not what you see experimentally at all. Okay, so when you twist two sheets of graphene, there's a lot of relaxation, it's called. And just to illustrate this, so this is actually what it will look like. Okay, so since the AB stacking of the graphene is much more stable, what you actually see is that you have these like large, well, maybe let's call them bays, where you just have this mismatch between blue and red. Okay, unlike what you see here. So these are all. So this is some picture I've taken out of another paper, but so this is essentially what it will look like for small twisting angles. Okay, so this idea of I just have two lattices and I mathematically consider a model that is just that just takes into account what the lattice structure would look like. Is maybe not the most realistic one in order to capture the physics here, okay? Because this is actually what the moire pattern will look like experimentally. And so a lot of progress has actually been made also by mathematicians on this idea of, well, what kind of effects are there that cause this relaxation actually to happen, apart from maybe this like basic idea that AB is just more stable than AA. And so I just want to maybe in broad terms refer to the work of Carr, Caxiras, Laskin, and Massart, who, and then in later works, developed this idea of what is actually relaxation much further. And now there's a wide range of models that take more or less important things into account there. Okay. So I'm going to talk less maybe about this effect of relaxation. I just wanted to mention it to you so that you have an idea of what is actually happening there. What I'm going to talk about is some analysis of some effective model that describes these materials, okay? And so in practice, what we have is that we have some either semi-metal like graphene or some semiconductors, and these are, for example, these TMDs. So this means you have some transition metal and then a dichalcogenide like silene. And based on that, you take so usually when people talk about moire materials, it's either based on something like this, a semi-metal or a semiconductor that then gets twisted or displaced in some sense. And the Hamiltonian that has become famous to sort of describe what is actually happening in these materials, at least effective for a one-body model, is called the Bistritzer-McDonald Hamiltonian. Okay, and this one was proposed in 2011 before the field was somewhat fashionable. And in some sense, it's an effective Hamiltonian that has this, well, in broad terms, it has this idea that, well, there's something that describes my semi-metal or my semiconductor that I'm talking about. Okay, and that's described by this operator here. So some differential operator essentially. And then there's the coupling between the two lattices, okay? And that one operates on the length scale theta x, because I was just telling you that this moire length scale is essentially like 1 over the twisting angle, okay? So that's why it looks like that. And so this is, in some sense, where it's important that we talk about semi-metals or semiconductors, because, for example, for the graphene, maybe you've heard of that graphene is, it exhibits these kind of Dirac cones. Maybe that, if that doesn't mean anything to you, then just ignore that comment. But the idea is that you want something where sort of the effective band structure at the energy range that you're interested in is described just by some differential operator and not by some effective potential on the other hand, right? So observe that there's no potential here in this Hamiltonian that somehow acts on the individual lattice length scale. There's one on the moire length scale and one differential operator that has something to do with the original material that I'm working with, but there's nothing for length scale in between. And so okay, so that was the initial proposal by Bistritzer-McDonald. now there's been quite some work on trying to understand where that model actually comes from. So again, we have some work by Massad and Carr on this, maybe more from a also quite, I would say, in between sort of mathematics and physics. Then Conseil Garrigue Gontier, that was in 2022. Then work by Alex Watson and collaborators. And I saw, I think maybe a couple of days ago, that actually that paper won the Journal of Mathematical Physics Award for well, I think it was published in 2023, so then for last year. And so that's a very nice paper that essentially follows, in some sense, a bit this idea of saying, well, I want to understand my Bistritzer-MacDonald Hamiltonian, where it comes from. I consider some kind of wave packets that start close to particular points in the band structure of my semi-metals or my semiconductors. I try to understand for, let's say, some type binding model, how that wave packet evolves. And what I find is that, hey, this is actually pretty close to what a Bistritzer-MacDonald Hamiltonian would give me. Okay, so that's a dynamical result that somehow says that certain wave packets, particularly localized in Brion zone, they will evolve essentially according to the Bistritzer-MacDonald Hamiltonian. And that model or that paper, it is mostly concerned with graphene, but as far as I understand, it would also extend to maybe some more general materials. And then there's also some work by Conseil and Meng, and that work, if I remember correctly, it's some sort of semi-classical work which says that for small twisting angles, which is essentially what people are concerned about mostly, the Bistritzer-MacDonald Hamiltonian in some sense is a good effective model in some sort of density of states measured distance. Okay, so the density of states of the Bistritzer-MacDonald Hamiltonian actually describes something that is related to, let's say, a more complicated model like a type binding model. All right. So now, okay, so this is also before the sort of wave of moire materials started. But this, I think, comes back to this idea that sort of large fundamental domains are actually something that is quite important. Okay, so that's already something that is interesting, independent of what we might learn about magic angles afterwards. And the basic question was, well, can we actually so if you want to describe an electron that is confined to, let's say, a Z2 lattice in a magnetic field, if you study so you have a constant magnetic field that is sort of perpendicular to a Z2 lattice, and the electron is confined to the Z2 lattice, then the spectral structure is quite famously known as the sort of Hofstadter butterfly. Okay, so the Hofstadter butterfly essentially. So here we're plotting essentially energy, I guess, and here we're plotting the magnetic flux. Okay. And then the sort of fractal spectrum that is known as the Hofstadter butterfly, and these colors here, they are the Chern numbers in the sort of spectral gaps of the Hamiltonian. Okay, and it's in mathematical physics. I mean, there's an entire field that is sort of analyzing that effect, but experimentally, it was always basically impossible to actually measure this, and the reason is that in order to sort of see this something like this pattern here, so to measure these Chern numbers, you need quite a strong magnetic flux, right? And so this comes back to this issue with if you're working on sort of atomic distances, then the problem that you run into is that, well, you might have a strong magnetic field for whatever reason, but since your fundamental cell is so small, your magnetic flux will automatically also be small, right? So you're not going to sort of go through this entire range of magnetic fluxes, and therefore it was always quite difficult to actually experimentally measure the Hofstadter butterfly, all right? But now this was sort of one first application of these moire materials, because if you have a small twisting angle, you get these large fundamental domains, and therefore you were able to see actually, or you're able to generate sort of large magnetic fluxes. And as a consequence, people sort of derived, so this was in 2012, something that sort of resembles, and I understand the resemblance is maybe not that obvious at first glance, but so people actually measured these sort of Chern numbers, and that should correspond to these Landau fans, people might call it, in the Hofstadter butterfly. Okay, so people sort of were experimentally able to measure these different Chern numbers. All right. So this is something that happened before, people really got interested in these moire materials. And then the interesting effect was measured in 2018. And so the setup is that, so what people did is that there's a particular angle, it's called the magic angle. And well, here it's 1.05 degrees, I guess. So for me, I mean, it suffices to know it's roughly 1 degree, so small angle. And at that angle, what people observed is that you see some very interesting many-body phenomena, I would say. So what people might call strongly correlated electron phenomena. And so what we see here is that, and sort of this is taken from the sort of experimental picture. So you have this, okay, so our moire material, right? I mean, I understand mathematically maybe not, right? But in Platonic reality, it is a sort of periodic material with a period given by this moire cell. And then as we change the number of electrons, okay, in the band structure, and I'll talk much more about the band structure afterwards, but as we sort of change the number of electrons, and then that's indicated by the sort of filling factor here, we see for very low temperatures, right, 1, 2, 3 Kelvin, we see a range of sort of different phases of condensed matter, right? So here we see a metallic phase, here we see a superconducting phase, and this was sort of the main effect. We see an insulating phase, the mod insulator phase, and then another metallic phase. And seeing this sort of superconductivity there, that was something that people got very excited about. And also from an experimental perspective, what was interesting is that, since you have, and I don't know, maybe this analogy might not be the most appropriate one, but since you have this sort of large fundamental, but this is, I guess, how I think about it. Since you have this large fundamental domain, right? It's easy to change the sort of filling factor experimentally. Just like maybe if you have a sink, and you have a large sink and you have to fill it with a bucket, right? It's easier than if you try to fill a glass, which is much smaller, right? So if you want to have half filling, then it's much easier to sort of tune these different filling factors and then maybe observe different phases. So what is interesting here is that we see all these different phases at this particular angle, okay? And my goal in some sense first will be to explain sort of in this sort of one particle picture what sort of interesting effect actually happens at this angle here that leads to some kind of understanding of where these things come from. So at the moment, I think it's fair to say that still the question of, why is there a superconducting phase, even in physics, is, mathematic is not that explored. So let alone that there's a mathematical understanding for why this happens. But in some sense, why there exists this magic angle, I mean, there's some understanding there, and I'm trying to explain maybe that in my talk. All right. So I think one of the main drivers in physics these days is really what is the real phase diagram of twisted bilayer graphene, okay? Okay, so something that is maybe a bit less fancy than superconductivity, but something that is easier to grasp, I think from a mathematical perspective, is the anomalous quantum Hall effect. So I guess we know the Hall effect from our high school physics classes. So the quantum Hall effect is the sort of quantized version of that, if you want. And the anomalous quantum Hall effect, so I think the anomalous Hall effect was already discovered by, well, Mr. Hall. But the anomalous quantum Hall effect, what that is about is that you essentially see an effect like the quantum Hall effect, but just in the absence of a magnetic field, okay? So think about it. So well, mathematically, I think we can easily understand this in terms of sort of Chern numbers. But in our case, so what we discover is, so here we're plotting the magnetic field being equal to 0, and we see sort of this, so for very small temperatures, we see this jump here in the resistivity, so for very low temperatures, and zero magnetic field essentially as a discovery of this anomalous quantum Hall effect in twisted bilayer graphene, okay? And well, so once you have the quantum Hall effect, the next thing that you might want to ask about is there also a version of that for the fractional quantum Hall effect? Okay, and what people noticed is that, well, the fractional quantum Hall effect, you can measure it actually in twisted bilayer graphene. So maybe don't press me on these experimental figures here. So it's more maybe important to understand a bit the story. So the fractional quantum Hall effect was then measured, but with an external magnetic field. And then the anomalous fractional quantum Hall effect, so the fractional quantum Hall effect without a magnetic field was not discovered in twisted bilayer graphene. But then what happened is that in these semiconductors, so these transition metal dichalcogenides actually, and this was last year, and it was sort of another sort of major point, I think, in this field, the anomalous fractional quantum Hall effect was discovered in in sort of this semiconductor here, and actually in twisted pentalayer graphene. Okay, so pentalayer just means that you have 5 layers of graphene stacked on top of each other. Okay, and yeah, so from a condensed matter physics perspective, that was also pretty interesting. And I think now another main question in the physics literature is, can one actually have this non-abelian anomalous fractional quantum Hall effect? So non-abelian because it has this sort of well, that's related to the structure, of course, of the fractional quantum Hall effect, but this interest in this particular one is due to this potential application in topological quantum computing. But I think, independent of the fractional quantum Hall effect, I think what sort of maybe my goal is to shed a bit of light on this anomalous quantum Hall effect as a sort of condensed matter phenomenon during my talk. So if we achieve that, then I think that's already pretty nice. Okay. Okay, so now this was a bit of background on what people observed. Now I wanna go to this effective one particle model, the Bistritzer-McDonald Hamiltonian, and then I want to explain what kind of mathematical analysis one can do there. All right, so I think I told you that the idea of this Bistritzer-McDonald Hamiltonian is that you have some kind of effective Hamiltonian for the, let's say, the semi-metal or the semiconductors. Okay, so that is for the individual layers, and that's just a differential operator. And then you have some interaction potential that is operating at the Moire length scale, right? The Moire cell, it's proportional to 1 over theta essentially. So that's this object here. And so for the graphene, I mean, well, there are a lot of not too difficult ways to do it and to sort of derive that, but due to time, I'll just skip that. So for the graphene, you can convince yourself that a certain energy in the band structure is actually described by a Dirac operator. Okay, so if you know that, then you might accept this, and otherwise, please also accept this just as a fact that certain energies are described by a Dirac operator in 2D. So what I'm doing here is that first my coordinates x, they are now 2, so that describes obviously my electron traveling through the 2D plane. But what I do for this talk, because I work with Dirac operators, is I sort of complexify the coordinates, and I work with a variable z, which is now just a complex number, okay? So in the following of my talk, z is just a complex number. It's a position of my electron traveling through the TBG system. All right. So if I just had 2 sheets of graphene that wouldn't talk to each other, then at least, in certain energy regimes, they would just be described by this Dirac operator on the diagonal, right? Because this is just 2 non-interacting sheets of graphene. Okay, perfect. So now what I also have is this interaction, right? I have some kind of interaction where the electron can tunnel essentially from one layer to the other. And my tunneling potential might depend on the region that I'm in. Okay, so if I'm in this AA region where we're sort of similar, so remember there was this AA and AB stacking. AA stacking meant essentially sort of similar atoms on top of each other. AB meant quite the opposite. And so my tunneling is then just, given by some effective potential, essentially it tells me the sort of hopping amplitude to move from, let's say, the upper to the lower layer in these particular regions, okay? So that's a bit the idea of this Hamiltonian. Okay, and so this is the Bistritzer-McDonald Hamiltonian then. So you do some rescaling here. This theta x, you just call it x again. Then you will have essentially a 1 over theta appearing in front of the differential operator. You multiply, you will have, what did I say? No, you do the chain of variables, you will have a theta in front of your differential operator. You divide by theta, and then what you get is back your differential operator, and you have a 1 over theta in front of the potentials, and this is parameter we just call alpha, okay? So alpha is 1 over the twisting angle, so small twisting angles means large alpha, okay? So this is sort of just a change of variables of this Hamiltonian here, and this is the object I'm looking at. And okay, so the Bistritzer-McDonald Hamiltonian, it consists of this operator here describing just the single, well, let's say semi-metal or semiconductor, in our case, the graphene. And then there's this hopping amplitude to go from the upper to the lower lattice and from the lower to the upper lattice, and the twisting angle appears at this parameter theta, okay? So that's as simple as it is. Okay. Now, I told you before that somehow when you have graphene, right, graphene tends to be, and this also happens for the Moire materials, as we saw in this one figure, graphene tends to exhibit these or prefer to be in this AB region, right, where the lattices don't align. And so one particular limit of this Bristol semi-Macdonald Hamiltonian that you can look at, and in some sense the only one where at least we ever felt to be able to make mathematical progress on the theory, because the results that we have for the Bristol semi-Macdonald Hamiltonian essentially then build up on results for this particular limit, is this so-called Carroll limit. Okay, so the Carroll limit says, well, okay, you have these AA regions, these BB regions, so where you perfectly align, but you just assume they're not there, and so you set these interactions equal to 0, and then what you get, so this one is equal to 0, this one is equal to 0, because they are more redundant, and then what you get is this kind of tunneling potential here, okay? So that's the only object that remains, and this model was then proposed in a Physics Review letter article by Tarnopolsky, Khrushchev, and Vishwanath, which is called Origin of Magic Angles in Twisted Bilayer Graphene, okay? So just to explain that, so what is the simplification here again? So we have this Carroll limit. We start from the Bistritzer-McDonald Hamiltonian, but we take this sort of tunneling potential. Then what you can show, and this is sort of the Carroll symmetry in this model, is that you can conjugate, once you put these diagonal entries in the tunneling potential equal to 0, you can get this off-diagonal operator, this off-diagonal Hamiltonian here, so just by unitary conjugation, which has this form d alpha star. And d alpha is the following operator, so it's 2dz bar, right? So z was our position variable, so a complexified position variable. And this is the tunneling potential that we have from these AB and BA regions, okay? And the twisting angle, remember that, is sort of, it has been conjugated to be in this parameter alpha, right? So alpha is 1 over the twisting angle, okay? So if you want small twisting angles, large alpha. And the tunneling potential, I mean, what is it supposed to satisfy? We've done this with scaling, so we're no longer working in this 1 over theta moire fundamental cell, but we've essentially we've reduced everything to a unit size fundamental cell. And so essentially what it has to satisfy are the symmetries of the honeycomb lattice. Okay, so the symmetries of the honeycomb lattice, of the triangular lattice if you want, they are a translational symmetry. Okay, and this is the translational symmetry written in complex coordinates with a third root of unity. So these are for omega 1 and omega 2, these are the two lattice vectors that span sort of the triangular lattice. And then you have a 2 pi over 3 rotational symmetry. Okay, so the only thing we assume about these potentials, so this is this AB and this BA potential, is that it satisfies these two symmetries. Okay, so that's the idea. And once we understand this Carroll model, I'll comment afterwards again on what happens for the model where we don't make this assumption that the diagonal is equal to 0, and I'll try to explain how one would put sort of this many-body interaction maybe into account as well to understand some of these condensed matter phenomena. Okay, but so for the moment, this is sort of the object that we want to focus on, this Carroll model. Okay, all right. So so you see, I mean, before I was already mentioning that. Well, when you twist these lattices, you might say, okay, is it commensable, is it incommensurable? But in experiments, this is maybe less of an issue because you have so strong relaxation effects that this mathematical notion might not necessarily make sense. Or maybe you would have to consider particularly designed cases where this is where you can actually see that and don't have relaxation effects take over. And so since this is actually a periodic Hamiltonian now, right? Periodic with respect to this, well, rescaled moire cell, so just essentially the triangular lattice, you can apply Bloch theory, right? Bloch theory says that if you have a periodic Hamiltonian acting on, let's say, L2 of the entire complex plane, right, and it has a periodicity, then you can reduce everything to the study on the fundamental domain of your lattice. So if this is our lattice gamma, the triangular lattice, with respect to which one we are periodic, then we can study our Hamiltonian just on that fundamental domain. The price that we have to pay is that we have to add the so-called quasi-momentum, which is sort of the Fourier variable that we get from looking at the Bloch transform, right? So we can conjugate Hamiltonian to something that acts on the simpler space, not on the entire complex plane anymore. But the price we have to pay is that now we have this additional parameter k floating around there, which comes in for the differential operator. Okay, so K is now in the dual lattice, and so I just want to show you now the basic effect where I show you the band structure of. So what this means is that I'm plotting the eigenvalues of this Hamiltonian parameterized by this parameter K, where now K, okay, just to illustrate this, I've taken a square sort of unit size fundamental domain, and I just show you, so since this Hamiltonian has this off-diagonal form, its spectrum is sort of symmetric with respect to zero. So what I'm showing you is the spectrum that is sort of in the upper, the positive real numbers, okay? And what you see is that there are certain angles, or certain alphas here, where this lowest band becomes entirely flat, okay? And so that is one thing that one is after here, because that somehow means that the kinetic energy of my electron traveling sort of through the entire structure, this one, well, it's apparently zero, right? Because there are these alphas for which this lowest band is completely zero. And what happens then is that the electron-electron interactions somehow can take over, okay? So that's why you see this sort of strongly correlated electron phenomena, because you have these cases where in some sense the kinetic energy of your electron is completely zero, okay? So that is the sort of basic effect that we're interested in this Hamiltonian here, understanding for what alpha, right? And alpha is somehow one of our twisting angle, does this phenomenon happen? So just to show you again, so this is the first one here, where this lowest band becomes completely flat. All right. All right, so let's try to understand how we can think about this. Okay, so what is it that we just saw? Well, we saw a flat band at zero. That means zero is an eigenvalue of all these HKs, so independent of what K we took, right? K was parameterizing so these were K was the X and Y axis, and we saw that the Z axis was always equal to zero for particular values of alpha, which was what was changing in the previous movie. And so if we have this flat band at energy zero, what this means is that zero is an eigenvalue of all this. And if we look at our operator, then what that actually means is that if this holds for all K, so that for all K, zero is an eigenvalue of this, then this means that all K are eigenvalues of d alpha, okay? And if all K are eigenvalues of d alpha, that means that the spectrum of d alpha is the entire complex plane, okay? So in some sense, we can sort of reformulate this, and this holds because d alpha is a Fredholm operator of index zero. So if K is an eigenvalue of d alpha, then K bar is an eigenvalue of d alpha star, right? So it cannot be that one happens but not the other. So we've reformulated this question of, what does it mean to have this flat band at energy zero, meaning that there's somehow no effective kinetic energy, meaning that we have this sort of magic angle, so this particular alpha where this effect happens. It's equivalent to saying that the spectrum of the alpha is the entire complex plane. Okay, and so really our first sort of result in this business was that, well, so there's this discrete set of values of alpha in the complex plane, and they don't have to be real, it's really in the complex plane, where the spectrum of the alpha, well, it changes between being something discrete, if you're not in this discrete set, so if alpha is not in this calligraphic A set, then you're discrete, so you're just 3 gamma star plus 0 minus I. And you can see that here. So if alpha, so this was alpha equals to 0, 3, then you see that you just have these like conical points here, and they intersect 0 at, so what I'm saying is that the lowest band somehow it intersects 0 at 2 distinct points, okay? And this is what you see. This is essentially the significance of this. So you're either in the setting, essentially all the time, or the spectrum of the alpha becomes the entire complex plane. Of course, it's a bit peculiar at first because the alpha itself, so let's just go back for a second so that maybe you don't forget what the alpha was. The alpha itself is an operator that depends very nicely on alpha, right? So it has this, it depends on alpha with this sort of linear dependence in the potentials. But for certain values of alpha, the spectrum of this really then becomes the entire complex plane. And that is the fact that we are somehow after in this sort of chiral limit. Okay. And then, okay, now, of course,
Dylan, I have a question. So does the flat band always, does the lowest flat band, does the lowest flat band always have energy zero? Or what is special about this zero?
okay, so I mean, okay, in principle, this is a perfect question. I mean, you could also ask why not. So zero, of course, is special because it means zero kinetic energy, right? So of course,
Yes.
you could also have a flat band at some other energy level, but that would not mean that it would just mean that okay, your electron can essentially have this sort of constant value of whatever it is.
Mhm.
So for the study, so we don't know actually if there are other energies at which you see these flat bands. I mean,
Okay, but if
yeah,
if we only look at the lowest band,
yes.
and then does it always have zero energy when it is flat?
Mm. So this Hamiltonian here, right?
Yeah.
It has the symmetry with respect to zero. So this entire figure that you see here is
Uh-huh.
also sort of, you also see it again for the negative energies, right? So in some sense, it's not the lowest band, but it's just the one
Okay.
where you have this sort of symmetry. So you have to think of this figure again projected,
Mhm.
down.
Mhm.
It's just that I'm not showing it, but then you would have these kind of conical intersections here, right?
Okay. So
It's
yeah.
just zero is a special value from physics, and it's somehow also the only one that we can analyze. So we don't know actually for higher energies how
Okay,
to
but
study.
anyway, zero comes from this symmetry.
That's
Okay.
right.
Thank you.
Right. Yes. Yes, that's right. So it comes really from this sort of off-diagonal form here. So that's very, very nice in some sense. And zero is always in the spectrum because you always have sort of these Dirac cones in some sense, because of this result here, that the spectrum of the alpha always contains, so there are always some k at which zero is an eigenvalue. But having a value of a twisting angle where for all k you have zero as an eigenvalue, that's quite an exception, okay? And okay, now you might say, well, this is all nice, but this is some kind of implicit characterization because how do you know what these alphas are? And so this is a bit, well, it takes certain symmetries into account and other things, but it turns out that one can somehow turn this sort of implicit characterization by saying, well, alpha is magic for us if the twisting angle is magic for us if the spectrum of the alpha is the entire complex plane. You can turn this implicit characterization into an explicit characterization by saying, well, alpha is magic if 1 over alpha is in the spectrum of this operator tk, and tk is this operator here. So it's 2dz bar minus k inverse, and then it has our tunneling potential, right? So this is the AB tunneling potential, u of z and u of minus z on the off diagonal. So let's look at this for a second. So it turns out, and this is sort of related maybe to this magic angle effect if you want, that the spectrum of tk, even though it isn't operated, obviously depends on k, the spectrum of this operator tk is independent of k as long as you choose k not in the dual lattice, which is the spectrum of this operator here. So we're studying this operator tk on the fundamental domain of our lattice, so L2 of C over gamma, okay? And this operator here, so since this is a compact domain, is a compact operator, the differential operator of order -1. And then we have these periodic potentials. So this is a compact operator. Its spectrum does not depend on k, but the operator tk is a non-normal operator, okay? So it has nice properties, and this is where sort of, for example, discreteness comes from because it's a compact operator. It does not depend on k, which is not obvious at first. It gives the magic angles, but it's not a normal operator. Okay, and so at first, since this is not a normal operator, you might say, well, I mean, there's an issue in the sense that it could be that zero is the only object in the spectrum of this operator tk. Okay, because it's not normal, this can happen, like for example, for the Volterra operator. I should say, now you might say, okay, maybe the Volterra operator is a bit of a contrived example and, it doesn't really happen in practice. If you try to do this entire business here, not for the triangular lattice, but for the square lattice, this is exactly what happens. So if you could ask, okay, what if I have some moire lattice that has some kind of square lattice symmetry? Well, you can essentially repeat this entire argument. You will just find, okay, there are no flat bands because tk in that case, the operator that you derive, it actually only has zero in its spectrum, so you just don't see any flat bands, okay? So there's, in some sense, something special happening about the sort of honeycomb lattice that we're studying here. If you try to repeat this for other lattices, you find certain obstructions. And so now to understand if there actually exist these magic angles, which we always saw in the movies, we would have to study this operator tk. Okay. So let me first try to illustrate what the spectrum of tk looks like. So tk is a compact operator, so I'm plotting now 1 over the spectrum of tk, right? So this is why, so this is the real the real axis, this is the imaginary axis, and the red dots here, they are the so let me just go back to explain. So 1 over alpha is in the spectrum of decay. 1 over alpha is essentially proportioning to the twisting angle. I'm plotting now 1 over the spectrum of decay, so I'm plotting alphas. Okay, so I'm plotting 1 over the sort of magic angles now because I'm plotting 1 over the spectrum of decay. And this is what you get. You see this sort of interesting sort of symmetric patterns or symmetries. Of course, you can understand from the symmetries of your model. But what is not obvious at first is why there's all this structure to it. Okay, and so the sort of magic angles that one is interested in, maybe in physics, let's say, are the ones on the real axis here. Okay, and they have this property. So these are 1 over the physical angles, if you want, and they have this property that they are more or less equidistantly spaced, apparently, which is also kind of curious, right? So the first one here is at 0.58 something. The next one is 2.2 something. And the distance seems to converge to some sort of, if you want, fixed ratio. Well, not fixed ratio, fixed difference of 1.51, slightly above 1.5, okay? So that's the effect that you see. So you want to understand, so just to summarize this entire discussion that we had so far, you want to understand where do these magic angles happen. And it turns out that they happen essentially in this Carroll limit, at least, essentially at equidistantly, well, the reciprocals are equidistantly spaced, and there seem to be infinitely many of them, and then there also seems to be some complex ones, and they are given essentially by 1 over, or the magic angles are given by the eigenvalues of this operator tk, and we're plotting here 1 over the eigenvalues of this operator tk, okay? But we're not interested necessarily in tk, we're interested in this Hamiltonian, which is, of course, self-adjoint. It's just that we want to understand for which parameters of alpha do we have these flat bands at energy 0, okay? So, so like I explained, I mean, for the square lattice, you see, you know, that unfortunately there are no magic angles. Initially, we were also struggling with that. In particular, we didn't prove that there exists a real magic angle, which is maybe the one that you might want to see in physics. But we showed there is something in the spectrum of this operator tk, which might be, you know, it might be a complex number. So when I say complex, I mean not a real number, something with a non-zero imaginary part. And the way we did this is that we computed the trace of this operator tk. So we raised tk to the power 4, we computed the trace of that, and then we got this number 72 pi over square root of 3. Since the trace is the sum of the eigenvalues, well, it means that there has to be a non-zero eigenvalue, because otherwise we wouldn't end up with that number. Hence, we concluded, okay, there has to be something in the spectrum of decay that is not just, you know, the zero element. And this is what you would see, for example, for the square lattice, is that all these powers of the traces would be equal to 0. Okay, so this was also, of course, a rather non-direct argument to see that. And then Michalowski and Alex Watson, they had some sort of nice, well, computer-assisted argument how they saw that there has to be actually maybe the first magic angle, which means the largest magic angle, also the one that you actually see sort of in experiments. And they used some sort of computer-assisted proof of that and followed, if you want, not this operator tk, but they followed more what was in this original physics paper by Anopolsky, Khrushchev, and Vishwanath. Okay, and so they saw that okay, there actually has to be something real in the spectrum of this operator tk in our language. Okay, then we got some help from Twistronics, who's a very sort of smart, and now he's a PhD student. So with his help, so here we computed the fourth power of the trace, but we were immediately not able to sort of generalize this. So with his help, we were then able to show that, well, if you compute essentially a trace of tk to any power 2p, what you find is that that trace is going to be pi over square root of 3 times some rational number, okay? So all these traces of tk raised to some power 2p, and it has to, p has to be larger than 1, so that this is a trace class operator. They're always of the form some fraction times pi over square root of 3, okay? And then essentially, because pi is transcendental, you can argue that there have to be infinitely many of these magic angles, okay? So if you assume there are finitely many, you could actually show that would lead to a contradiction to pi being transcendental, and this way you can conclude that there have to be infinitely many. And so in that article, we also have some sort of, I want to say maybe some kind of algorithm how to compute these first traces, and these are the numbers, okay? So sorry for maybe this convention, which is a bit confusing, but the idea is roughly that, okay, you can compute the first. So first you have this information, this sort of abstract information that the operator, the compact operator, gives you these magic angles. We can compute all its traces to any power 2p, where p is a natural number, and it's always this. And from this, you conclude there are infinitely many, but still that doesn't tell you at first that there has to be something real, because they could be all complex. And the way you show that there has to be something real is that you say, well, I can actually study the Fredholm determinant of this operator tk. If I show that it has a zero, then I can conclude from it that there has to be some real magic angle. And since the Taylor coefficients essentially of the Fredholm determinant are given by traces, well, so if you know enough traces, you can show that this determinant actually has a zero. Okay, and so this is how we concluded that there has to be actually this real magic angle, which is simple. It's a simple eigenvalue, and I'll come to that in a second. And it's in this interval here. Okay, so sort of maybe comparable to this result, but here it rests on sort of this sort of explicit understanding of these traces. And of course, in some sense, we can compute finitely many traces, but we don't have a closed formula for all of them, because that always involves computing some residues. And so, for example, our traces don't allow us to understand, for example, this equidistant spacing here, why it occurs or what's happening. Okay. So I said it's a simple eigenvalue. There's an interesting effect which is related to the potential that you're choosing. So for the potential that I've shown you, which is the one that, it's the simplest one that satisfies all the symmetries. So here these are these, so I'm plotting essentially 1 over the twisting angle again, right? So that's similar to the plot that you saw before. The real ones, the real 1 over magic angle, so to say, they are essentially equidistantly spaced for this potential, and they are all simple eigenvalues of this operator tk. Okay, why am I emphasizing the simple? Well, because if you change the potential a bit, so you just choose another potential that satisfies also the same symmetries, you see that in that case, all these magic angles, so all these eigenvalues of tk, they're actually twofold degenerate. Okay, so they have a higher degeneracy, and what that means is that so before you have essentially these Dirac cones and they become flat, and the same happens from below, so you have 2 flat bands in total. Now what you will have is that you have 4 flat bands in total. Okay, sort of I'm illustrating this somewhat here. So when you choose the sort of new potential, what you will have is, well, you have these 2 bands, and then at certain magic angles, which are different from the old ones, you will see that all these 4 bands are then essentially flat. Okay, and you see that, for example, this effect of having these 4 bands, that's sort of well represented still in this Spitz-Macdonald Hamiltonian. So if you don't look at the scalar limit, then you see the sort of same effect happening. You see that you have sort of these 4 bands sort of cluttered together, and then there's a gap to the remaining ones. And just to show you that this effect of, what are the magic angles, what's their multiplicity, is very sensitive towards which kind of potential do you choose, independent of symmetries. I just want to show you some movie where red dot means 2 flat bands, so simple magic angle, simple eigenvalue of tk, and blue means 4 flat bands, twofold degenerate eigenvalue of tk. And I'm choosing the potentials u of theta, so this is just some potentials that satisfy the right symmetries, and I'm going to vary this parameter theta, and as it varies, so the potentials always sort of satisfy the right symmetries. But as it varies, you see that, well, this effect of 2 flat bands and 4 flat bands, that's not very stable, unfortunately. And also the equidistribution on the real axis, that's very special for these particular cases. So here I'm varying this parameter theta in here, and now you see that, okay, sometimes, you have blue here, sometimes now you have only blue, now you have the red ones back again. Now there would be some blue ones again here, the equidistribution, right? It's also not very robust. So all these effects, they seem to rely very much on the particular potential that you choose, and not the symmetries in some sense. All right, but we do understand these multiplicities to a certain extent, and because everything here in this picture is either 2 flat bands or 4 flat bands, so you either see magic angles that have 2 flat bands or 4 flat bands in your Hamiltonian, and that is essentially something we can prove. So well, it rests again on the traces, but maybe for time reasons, let me sort of skip that discussion. So what we have is essentially an argument saying that if you choose a generic potential, right, a generic tunneling potential, it satisfies all the symmetries. And okay, there's some caveats on what you can choose exactly, but let me sort of gloss over that. Then what you find is that you will either have 2 or 4 flat bands generically. So so you choose your generic sort of potential. It will have either, so if you then study the magic angles, they will either have 2 or 4-fold degeneracy, so the flat bands of your Hamiltonian, and these flat bands. So you can package them in 2 of them that will have a Chern number +1, and 2 of them that will have a Chern number -1. Okay, and the fact that you have these non-zero Chern numbers is now quite important to understand this anomalous quantum Hall effect, because there's of course this connection between the quantum Hall effect and the Chern numbers. But for the moment, this is unclear because, well, if we have 2 and 4 bands and one bunch of them has Chern number +1, the other bunch has Chern number -1, they're all the same energy, you might say, well, then the total Chern number 0 and nothing happens, right? And this is now sort of important where sort of these many-body interactions come in, or sort of this is where the flat bands are useful, because now these strongly correlated electron phenomena, and that's a bit the idea, they sort of push you either in, they say that if you have sort of half filling of these 2 or 4 flat bands, then either you want to be just in the Chern minus sector or in -1 sector or in the Chern +1 sector, okay? That's a bit the argument, and I'll comment on that at the very end. But so this is sort of important to understand. Now you have a sort of 2 and 4 flat bands. They're at 0 energy. That's what generically happens here. The Chern number, it's plus or -1, depending on how you package them together. So the total Chern number is 0. So if you have 2 flat bands, one of them will have essentially Chern number +1, the other one -1, but they're the same energy. And for 4, 2 will have +1, 2 will have -1, and in total it's again 0, but everything happens at the same energy level. Okay? All right. This is sort of interesting because you might, and this is also an effect that sort of, I mean, I don't know where it was first discovered, so let me just comment briefly on that. So now you might say, okay, there doesn't seem to be any distinction between having 2 flat bands and 4 flat bands. And that's true. So because, well, both of them can happen, but they have the same Chern number. So is there sort of a difference in that? And the answer is that topologically not, right? But what is different is something that is called fragile topology. So fragile topology in the fact that it's a bit counterintuitive maybe for people in condensed matter physics, because all these topological effects, like, I don't know, Baguette correspondence, let's say, they're supposed to be robust under any kind of perturbations. So fragile topology essentially asks about, and maybe that's a sort of side comment now for people that are interested in this. Fragile topology asks about, so Chern numbers have an effect. So if you have a bundle, your Bloch bundle, let's say, or your bundle associated to the eigenfunctions of your flat band, and you associate a Chern number to that, you can ask, well, what does that imply actually for the original Hamiltonian? And for the original Hamiltonian, it implies something on the so-called Wannier basis. So the Wannier basis is essentially a basis of functions that are sort of, well, it's a basis of functions that are related to each other by translations. And if you have a Chern number that is 0, this Wannier basis, you can essentially pick it exponentially localized, okay? But if your Chern number is non-zero, there's an obstruction to doing that, and then your Wannier functions, well, you cannot choose them in the same way. Well, here in this business, our total Chern number is 0, right? Because ±1, if you add it together, is 0. So you can choose a Wannier basis that is exponentially localized. But then if you ask it sort of the Wannier basis to satisfy certain symmetries, and people here are interested in particular in one symmetry, which is the C2T symmetry. So you flip sort of coordinates and you do a time reversal, so a complex conjugation. So that's the only thing this symmetry does. If you want your Wannier basis to satisfy this as well, then it turns out that there's a difference between these 2 and 4 flat bands. And that's what fragile topology is about. It's somehow about the effect of choosing a Wannier basis that satisfies certain symmetries. So in the case of 2 flat bands, you're not going to be able to do that, choosing a Wannier basis that satisfies the C2T symmetry, whereas in the case of 4 flat bands, you are. So there are some sort of nuanced differences that are also important for then other phenomena between these 2 cases, but in broad terms, this is sort of what happens in this current model. I just briefly want to comment on what happens beyond this Cal model, since I've spent so much time on it. So beyond the Cal model, remember that the Cal model meant that we don't have these regions of AA and BB interactions, right? So we put them equal to 0, because we say, well, it's, the other one is the more stable one, and that's okay, but maybe putting it equal to 0 is a sort of strong assumption. So what happens then if we have this lambda parameter here, right, to sort of tune the other potential if you want? Well, we saw that we have these sort of equidistant spacing of magic angles in the Carroll model, which corresponds to lambda equal to 0. So that's here, right? And what I'm plotting here is the Fermi velocity. So I'm plotting the sort of first derivative of my Dirac cone, okay, in this full model. And so if I'm at this first magic angle and I'm plotting the Fermi velocity, the log of it, then as I turn on lambda, actually it turns out the first magic angle is quite stable. The one that I see in the Carroll model is quite stable in the Bistritzer-McDonald Hamiltonian, in the sense that you see a perfect straight line here, right? It goes up until 1, so essentially this is 0.58. So even choosing this one much larger than the original one, you see this very low number here, minus 18, which means essentially the Dirac cones on this full model, you will not see flat bands, but what you see is that the Dirac cone essentially becomes, it's not there, it just becomes quadratic. So that's the sign of a magic angle, that you have a quadratic dispersion relation rather than a linear one. All right. And then together with Solomon Quinn, Zhongkai Tao, Alex Watson, and Mengchuan Yang, we were actually able to show that. We showed that, well, there's this locally finite family of points and curves such that the full Bistritzer-McDonald Hamiltonian, it only exhibits these Dirac points outside of this set. Okay, so outside of a set of curves and points, what we see here, we will always have these perfect Dirac cones. Okay, and this is where you see, so the green color is essentially where you don't have this effect. And well, what about sort of this straight line? Can we understand why these things are stable? And the answer is yes. So magic angles from the Carroll limit, in some sense, so this is sort of now just in rough terms, just to avoid sort of technical details here. So the magic angles from the Carroll limit, they persist on approximately straight lines, so meaning the first derivative vanishes. And so what you see in the Bistritzer-McDonald Hamiltonian is that if you don't have a magic angle, you have this Dirac cone. If you have a magic angle, you don't have a flat band, but you have some quadratic dispersion relation, okay? And what also sort of follows from just this sort of topological argument is that when you have these, so when you go from a region where you're not at a magic angle, meaning now for this full model, you don't have this quadratic dispersion relation to a quadratic dispersion relation, sort of from winding number considerations, how they're related to the Euler number, you can conclude that actually you have to have more band intersections, right? So remember this Carroll limit, we had these two Dirac points all the time, and then the band became flat. So here in this full Bistritzer-McDonald Hamiltonian, as we get these quadratic dispersion relations, what happens is that we'll have to have more band crossings because of sort of topological considerations. So what happens here as we approach these sort of quadratic regions where we have initially maybe some cones, is that we will go through a phase like this where essentially it looks like really the band is flat because you have more intersections, or flat in some areas, okay? So this is what happens in the full Bistritzer-McDonald Hamiltonian. Of course, here I'm just giving you a short or a small sort of snippet of what happens really for the entire band, which is what you see here, okay? Right, so let me maybe finish with this last slide by describing how some of this is related to sort of many-body physics. And it's like in PDEs, right? I mean, linear PDEs we understand quite well. Nonlinear PDEs, well, we usually don't, unless we are at exceptional cases, which we understand well. Here it's a bit the same. I would say that this Bistritzer-McDonald Hamiltonian, I think now the mathematical understanding is better. But in the many-body world, I mean, very few things are explored. And so maybe that's the analogy. So if we think of this as the kinetic energy, the Bistritzer-McDonald Hamiltonian we're describing right now, then okay, if we have this flat band, as I was trying to tell you, this means that now we can focus on these electron-electron interactions. So why can we do this? Well, one argument that maybe, mathematical argument that one can bring forward is that in this Carroll limit at least, what you can show is that when you have these flat bands, then there's actually a spectral gap to all other bands. So what physicists like to do when they do some how should I say, analytical arguments, let's say, on this is that they say, well, I consider sort of my electron being confined to this sort of spectral subspace that is sort of given by these Bloch eigenfunctions that are associated to the flat bands. Okay, so my electron sort of lives in there, and then I put some sort of electron interaction on top of that. So you're confined to this sort of small subspace of flat bands if you want, and then you have some interaction on top of that, and you can argue that that's reasonable because of the spectral gap. It turns out that there something special happens, and this comes back to this story about the anomalous quantum Hall effect that I was trying to tell you in the beginning, which maybe one can understand to a certain extent. When you have this half filling, right? So we have these two flat bands, let's say. One of them has Chern number +1, one of them has Chern number -1, if you pick them in a nice way. Now, if you only fill them half, right? And it could still be that, well, you wouldn't see anything interesting in terms of quantum Hall effect, but there's this idea that when you're at half filling, then actually what happens is that you have some sort of ferromagnetic, and I understand this is very vague, but I just want to give you some sort of outlook on how to think about this maybe. So if you have half filling, then what you have is some kind of ferromagnetic ground state of the interacting one. So you confine yourself to the sort of flat band subspace, you put some interaction on top of that. It turns out that the ferromagnetic one is the ground state, when ferromagnetic here means that you fill essentially half of one of these bands completely. And this way you can interpret, okay, maybe the sort of anomalous quantum Hall effect appears because sort of energetically favored, at least if you choose the right model in some sense to model this effect, which of course has many, how should I say, it has many assumptions. But this way you end up with these like non-zero Chern numbers. But the idea is that, okay, the effects that you see, even this anomalous quantum Hall effect, the Chern numbers you can compute, but in order to see something interesting, you need the many-body interaction, and why you don't have this in graphene is because you don't have the kinetic energy equal to 0, for instance, right? And so if you want to read on that, I mean, since I've not really explained this really well, so this is the original physics paper, and then together with Kevin Stubbs and Lin Lin, we also have some sort of mathematical, maybe not just a version of that, but some mathematical paper. But this is the sort of original paper that proposed sort of a certain Hamiltonian that analyzes this. Okay, so thank you very much. So maybe I finish with my last slide. I guess still sort of finishing right after 1 hour, so maybe that's good. Thank you very much for your attention.
Thank you very much, Simon, for this lovely talk. We have some time for questions, so if you have any questions, please unmute yourself and you can ask.
Yeah, can I ask then?
Please.
Yes, there are some, but okay, so you mentioned that if you have the square lattice symmetry, then you don't see all these fancy things.
Mhm.
So is there any intuitive explanation for this difference between triangular symmetry and the square symmetry?
Not that I would understand. I mean, so to me this was a natural question, and really it was how should I say, surprising that it happened that there's nothing or that there are no magic angles in that case. What you of course need is and somehow there are not that many lattices you can check, because what you need in order to sort of set up this entire apparatus, so to say, is you need you need a lattice, so you need a translational symmetry, but you also need a rotational symmetry, right? And then the number of lattices that can that have this property are sort of limited. And so to me, there was no real reason why the square lattice showed this phenomenon. So this was actually something that a student was looking into, and I would have also guessed that there should be magic angles there, but I just don't understand. So this operator TK is just a nilpotent operator in that case, but I don't understand why, so to say, what happens with that, what is different with that lattice compared to this one here.
Yeah, thank you. Very interesting.
Are any further questions? There's a question in the chat by Ali Reza Jazani that says, have you studied how the Berry phase would change with the adding and twisting of layers?
Have I studied how the Berry phase would change with the adding and twisting of layers? So you mean if you add more layers? So, I mean, I was, for example, saying that there's this penta layer, right, um, which has the effect that, which shows, for example, this fractional anomalous quantum Hall effect, and it consists essentially of 5 layers. So yes, I mean, a lot of people are looking at sort of more layers just because they observe more sort of physics phenomena. What in general happens there is that you can see sort of different Chern numbers. This is known in a version that is called, so just as a pointer, if you look for what is called helical trilayer, it's a particular type of stacking of trilayer. So 3 layers of graphene. There you see, for example, Chern numbers 2, which you don't see in this in this in this twisted bilayer. So you can see sort of higher Chern numbers if you add more layers. That's possible, but it depends very much on the configurations you choose. Just because you have all of a sudden so much freedom, it's not it's not true that just because you have more layers, all of a sudden you have higher Chern numbers. It really depends on the configurations. Yes.
And I suspect that maybe experimentally it must be very difficult to tune the twisting angles for multiple layers.
Um, that is a good question. I mean, sometimes the problem is that I think these papers that you sometimes read on twisted trilayer is that they claim that somehow it's maybe even easier because I don't know. But yeah, I mean, I don't know, but I think that experimentally it's certainly something that is explored. So I think that I mean these multiple layers, it's not just how should I say, not as weird as we might think. So it's certainly something people look into. Whether it's easy or not, I actually don't know.
Well, thank you. Are there any further questions?
Yeah,
It
can I
doesn't
ask
seem
one more?
Yes,
So if
please.
you have this table of values of alpha starting from 0.58 or something.
That's right. Let me
Yes,
go there.
yeah, so is this for special UZ or is this universal in some sense?
It's yes. So this is for the one that, how should I say, the simplest one that satisfies all the symmetries you need, right? So you
Okay.
take the low Fourier modes and you
Mm-hmm.
just patch them together so that all the symmetries are satisfied. That's the values that you get.
Uh-huh.
Once you change your potential,
Yeah, yeah, yeah,
um,
yeah.
it's essentially this movie, right, where all of a sudden everything
Mhm.
changes as well. So
Yeah, but
in that
still the symmetry is preserved.
the symmetry is preserved, right?
Okay,
But really these values are not
uh-huh.
universal.
Okay. So you have this theorem about 0.58 or something, but it depends on the potential.
It depends on the potential. It turns
Uh-huh.
out that actually this value, so if you put in all these right numbers, then it's actually it comes actually pretty close to the real one.
Uh-huh. Okay, and what happens if this K gets larger and larger? Does this continue forever? Or
I mean, yes, we have not proven this, but it seems that way, right? So it
oh, yeah.
seems that there are really infinitely many on the real axis. So we know that there are infinitely many in total by this weird
Oh,
price transcendental argument, but we don't know why this sort of uh,
so it
uh,
means that you have smaller and smaller magic angles, actually.
that's right. But on the other hand, experimentally, there's some sort of obstruction to this, which is that if you look at very small twisting angles, then
Oh.
this relaxation
Mm,
effect becomes
mm-hmm,
stronger. Once
mm-hmm,
the relaxation effect becomes stronger, your
mm,
potential essentially has to have more Fourier modes capture to
mm.
capture the structure because it's
Yes, yes.
essentially like a
Mhm,
step function here, right? So somehow the potential would have to be changed as you
mhm,
change the angle. That's a bit
mhm,
the idea
mhm.
for these smaller angles.
Uh-huh. So do you see this one? No, I saw I forgot it is 1 degree or whatever. Do you see that one in your table of alpha or
That's right. So the first one is essentially pretty close to that one. That's right.
uh-huh. Hmm.
So the largest one is captured well, and then these lower ones, I guess
Hmm.
they are there. You have this effect of the potential just not being the right one.
Okay, thank you.
Thank you very much. I guess as time is running, unless there are any further questions, we can conclude the formal part of this seminar. I hope that you'll all join us again in 2 weeks when we'll have a talk by Angela Capel about thermalization and many-body quantum mechanics, and I hope to see you all there.